In this work, we propose a pair of metrics that allow for reliable evaluation of the performance of a generative model. With the generative model, we aim to learn the underlying distribution of the data, and with an evaluation metric, we aim to differentiate a good performing model from a bad one. Towards this, the community currently relies on FID score, which is shown to correlate with good and bad judgment by human. We see that the better looking set of images on the right gets a better FID score than the one on the left. However, there are two aspects of generation performance: fidelity, how realistic the data looks, and diversity, how well are the variations of the data captured by the generator. So does FID capture fidelity? And here we see that the better looking images on the right get a better FID score than the one on the left. Does FID capture diversity? And again, we see that the more rich set on the right gets a better FID score than the one on the left. However, when two different models get the same FID score, it's not possible to rank which is more diverse and which is more realistic without manually looking at the images. To diagnose these properties, precision and recall metrics have been proposed. Precision measures among fake samples what proportion of them lie close to the real manifold, and recall symmetrically measures that among real samples, which proportion of them lie close to the fake manifold. And here, closeness is defined in terms of a k-nearest radii. So this point lies inside the manifold, and this one lies outside. Let's see how this is calculated. Purple are our data points from our data set, and green is something the generator would have outputted. As a first step, we make a k-nearest neighbor approximate of our manifold. And now of the 6 points from the generator, we measure how many of them lie in this manifold. So 2 out of the 6 points land here, so our precision is 2 divided by 6. Recall is symmetrically calculated, and we generate the manifold on the fake samples. And now we measure how many of the real points fall in this manifold. We see 7 of the 9 points fall in the manifold, so our recall is 7 divided by 9. So precision and recall mathematically are defined as precision is a summation over all the generated points with an indicator function that's 1 if a point is close to the real manifold. And recall is symmetrically done for the real samples. So fundamentally, precision and recall capture diversity and fidelity. However, we will talk about some of fundamental problems with these metrics. When we have two disjoint set of data points with precision and recall in its current form, we would detect that an overlap of 0% is in order. However, if we have even a single outlier near the second distribution, now if we calculate our manifold, we see that its nearest neighbor is all the way here. And when we calculate the metrics on this manifold, we calculate a perfect overlap, even though the distributions are disjoint. Let's see what happens when the distributions are actually overlapping. So in this example, when we measure the precision and recall, we get a value close to 63%. This is very far from the ideal value of 100%, and this is problematic. This property and problem extends to other hyperparameters with the model. So the expected value depends on the number of samples, the feature dimension used for calculation, the nearest neighbor used for calculation, and the family of distribution our embeddings come from. Finally, the diversity metric is calculated based on a manifold approximate on the fake samples. These samples can be unstable from a generator, and this would need to be calculated for every model and every checkpoint. In order to address these problems, we propose density and coverage that fix these issues. We first fix precision with our fidelity metric called diversity. With precision, we are first calculating our nearest neighbor ball. And for the manifold, now it's a union over all these regions to get a manifold that's uniform in all the regions. However, with diversity, we again have the same disks, but now we are doing a superposition where these dense regions of the manifold are scored higher than these sparse regions. Now let's look at this visually. So if we calculate precision in this example, we would detect basically that everything is inside the manifold. So our precision is 100%. Let's do the same thing for diversity. We see that 4 of these points land in only one hypersphere, so they get a score of 1. And one sample lands in a dense region with 3 hyperspheres, so it gets a score of 3. Now our density is a summation over these scores, normalized by the k and the number of samples, 6, and we get a density of 58%. If we look at this mathematically, compared to precision, density is a summation over all the generated points, and for every point, we iterate over all the real points and see how many of the real points are close to our generated sample. This is normalized by k and the number of generated points. Now let's fix our diversity metric. For recall, we calculate our metric on a manifold of fake samples. With coverage, our proposed metric, we instead build a manifold on the real samples. This has the first benefit that this is more stable, as this is not changed over different checkpoints. And this manifold is computed only once per data set, so for every model and every checkpoint, you're always comparing against the same thing. Let's see how this is calculated visually. So for this example, for recall, we would build our manifold or on the fake samples. And now we see how many of the real points fall in this manifold. So we see everything falls inside, and a recall is 100%. With coverage, now we build our manifold on these real samples. And for all these hyperspheres, we see how many of them are populated by at least one generated point. And we see that 3 of the 7 hyperspheres are populated, so our coverage is now 3 divided by 7, or 43%. Mathematically, compared to recall, now coverage is a summation over all the real points with an indicator function that's 1 if an hypersphere contains at least one generated point. Our metrics have some nice theoretical properties. The most important one is that for identical real and fake distributions, we are able to derive the expected behavior. The expected value of density in this case is 1, and the expected value of coverage is this expression, which is 1 or close to 1 for sufficiently large m and nk. A very nice property here is that this is independent of the distribution type or the distribution dimensionality. We would like to point out that such an estimate does not exist for precision and recall as shown in our manuscript. So if we see the hyperparameter analysis from before, when we plot our density and coverage on the same graph, we see that our values are stable for number of samples, feature dimension, and the embedding space. And our value for coverage is close to 1 for sufficiently large k. This is our criteria to select our hyperparameters. So for hyperparameter selection, we choose m and n to be sufficiently large that our expected value is approximated by 1 minus 2 to the power negative k. We set m and n equals to 10,000, and we increase the value of k until we're able to detect at least 95% match for identical distributions. This is calculated at k equals to 5, which is our selected hyperparameter. Now let's analyze our metrics with some real data. For the first set of experiments, we show the robustness to outlier by training a style GAN on SLAB A dataset. We generate a large number of samples, and we divide it into inliers and outlier based on the point on the data's nearest neighbor. In the start of the experiment, we have no outliers in the set, and we gradually add the outliers to see how our diversity metrics change. In this example, we see that as the ratio of outlier is increasing, our recall metric explodes by 12%, while our coverage is relatively stable. For the next set of experiment, we simulate a mode dropping scenario. So initially, our real and fake samples consist of equal representation of MNIST digits. At each successive iteration, we increase the percentage of zeros in our set, until our second set only consists of the digit 0. In this setting, we notice that the value of recall does not change until everything is dropped. However, coverage shows a steady decline, showing the user that something is wrong with the generator and maybe we should look at the model. For the next set of experiment, we show the fidelity-diversity trade-off by using the truncation technique on a generative model. For this, we truncate the latent space of a style gain and generate samples at different fidelity and diversity. We see as the truncation increases, the images get more diverse and less realistic. We see in these graphs that the fidelity metrics are able to capture that the fidelity is decreasing as the value of psi is increasing. We also see that the diversity metrics, recall and coverage, are increasing as our truncation value is increasing. Let's talk about another part of our evaluation pipeline, which is the embedding space. Distances are not meaningful in the pixel domain, so for evaluation, we embed our images into an embedding space. The community currently relies on ImageNet pre-trained models, and these models are trained on realistic images from ImageNet, which tend to represent the natural world around us. But as generative models get more popular and their application is increasing in other domains like medical or sound generation, we hypothesize that these embeddings will not lead to fair evaluation. This can be something as simple as an MNIST or something as complex as the spectrograms of generated sound. In order to address this limitation, we propose to use a randomly initialized CNN as an embedding function. This has a nice benefit that this is not conditioned to any particular dataset. This works as this is sort of a nonlinear random projection on the set of the images. And this is shown in previous work that such an embedding space can be used for perceptual distance or image restoration. Some related work from CVPI 18 hypothesized that the CNN architecture in this case acts like a prior on the set of images. So let's look at our truncation experiment from before. So now instead of the VGG16 trained on ImageNet that we used before, let's initialize this embedding space randomly and calculate our metrics again. Under this random 4096 dimensional space, we see that the metrics, fidelity and diversity, are still able to capture the trade-off, even though the space was not trained on any dataset. Since we are not bounded by training it anymore, we don't have to calculate this at a high dimensional space like 4000. We can simply replace the last layer with something smaller, like 64. And under this 64-dimensional space, which is randomly initialized, we see that we are still able to capture the fidelity and diversity trade-off in all the metrics. As we move away from natural images, this set of experiment uses MNIST and trains a DC GAN. We see that our model has learned a good representation of the digits and is outputting all the classes. Let's calculate the metrics using an ImageNet embedding space. We see that our fidelity and diversity metrics rank this model to be performing very poorly, and this does not agree with our human judgment. Let's calculate this with our randomly initialized network, and we get values that are more realistic with our human judgment. Let's move away from images to sound generation. And in this example, we use a baseline waveGAN for sound generation. This is trained on a dataset which is similar to MNIST and consists of digits from 0 to 9. The real samples sound something like now,
8, 5,
and the fake samples sound something like
3, 6.
Now, when we calculate our metrics using the trained embedding space, we see that our diversity is close to 0, which would indicate a mode collapse. This is not in agreement with our human judgment. Let's calculate the same thing with a random embedding space. Again, we get values that more closely align with our human judgment. To conclude our presentation, we show that fidelity and diversity metrics are a useful diagnostic tool for performance of a generative model. Towards this, the metrics precision and recall have some fundamental issues. To address these issues, we propose density and coverage that have nice analytical properties. And we raise community's attention to another component of the pipeline, which is the embedding space. And we propose to use a randomly initialized CNN as we move away from natural images. Thank you for listening to our presentation. Our work is open source on GitHub, and you can install it from pip and use it right away. Thank you.